Hi, my name is Seema. This is my Module 3 presentation. So first off, I just want to start by introducing the data, and we're going to be doing that by taking a look at the describe function. So we can see we have 4 y variables, 7 x variables, and then 8 f variables. So just going in order, we can look at the y variables first. Most have a mean that's close to 0, except for y4 that's showing a very high mean of 106. And then Y4 just like kind of continuously shows variability. It has a high standard deviation of 88, a wide range from like -55 to 332. So that's telling us that maybe Y4 is measured on a different scale than the other variables. Then we have our X variables. Their means are also pretty close to 0, and they range from like -0.5 to 0.6, so they have pretty consistent standard deviations, and those standard deviations tend to be between 1 and 2. So it does appear to be mostly balanced. And then lastly, we have our f variables that appear to be categorical just based off the patterns that we have, and their means looks like they're about around 0.5, and standard deviations also around like 0.5, 0.51. So just kind of off the bat, like looking at this, we can see F3 kind of stands out because it does have a higher mean and standard deviation. But just kind of moving on to kurtosis, we can see that most of the values are negative. So that tells us that there are a flatter distribution than normal. Okay. Okay, so now I want to talk about reliability, and here we are looking at the results of our x variables, the reliability of our x variables. So first we have our raw alpha, which is our Cronbach alpha coefficient. We have a value of 0.58, and this is suggesting moderate reliability. Then we have our STD alpha, taking into account the differences of variances of our variables, and it's a little bit lower with a value of 0.53, telling us that our reliability is fairly low. Then moving on to the G6, we have, this is another reliability estimate, and we have a value of 0.67, telling us that the values are intercorrelated and leading us to see that there is that we have decent consistency within our values. Average R is talking about the correlation of each item with the total score of the other item. So 0.14 is a low score, and that's telling us that the individual items do not correlate well within the total scale. Then ASE, we have our standard error of the alpha estimate, telling us that the uncertainty in the estimate of Cronbach alpha, and the smaller the value, the more precise it is. So with a value of 0.11, that's pretty good. And then just taking a look at the mean and the standard deviation, we have a mean of 0.46 and a standard deviation of 0.91. And then we have our little table of the 95% confidence boundaries, and this is to help us get a sense of the uncertainty around the alpha coefficient, and we can take a look at the lower and upper bounds of that Cronbach alpha. Then we have we can look and see how dropping an item can affect the reliability, which in this case is our raw alpha. We can compare it to that number here. And we can see x2 and x7 are reversed because they have that negative next to the variable name. So we know those were were reversed. And then taking a look at x6, we can see an increase in the raw alpha with a value of 0.34, and that's leading us to conclude that the variables contribute significantly to the internal consistency, and they have a high correlation with the other items. And how we can tell this is because if we take a look at the table below and we take a look at the R drop for R6, there's a value of 0.7. So that's telling us that there's a high correlation. And then just to see like a flip side of the high correlation, to see a low correlation, we can see X7 has a low R drop of 0.25. And then just to kind of talk about R drop a little bit more, R drop is regarding the correlation of an item with the total score of the item. So that's why if we have an R drop of 0.7 for X6, it's showing a high correlation. And on the other hand, just to show another example, X2 has a very small R drop of 0.03. and a raw R value of 0.2. So that raw R value is telling us about the correlation of each variable with the total uncorrected score. Okay. All right. So here we're calculating the sum of values across each row for the x variables. So the first value we see is negative 1.979, and that's telling us the sum of the first row. Negative sum suggests that there are more negative values than positive, and then that lets us conclude that some were like reverse scores. Okay. A large positive sum value, like our last number, the 10.0299, tell us that the observation have relatively high score on the items. So then we have our correlation matrix here of our x values. First, we're just going to take a look down the diagonal, and we can see the distribution of each variable, as a histogram, and along with the fitted density curve. Excuse me. Excuse me. Okay. As I was saying, we have the histograms with the fitted density curve, and the plots below the diagonal, are scatter plots between the pairs of variables. We have big red dots on each of these graphs. Those represent the mean. The black circle around the red dot are focusing on the general trend and the spread of the data. And then we have a red line that is showing us the linear relationship. So looking at, we can look at x1. You can see there's a slightly right skewed. Like the x1 histogram, we can see it's slightly right skewed. We can look at x5's histogram and see that there's a symmetrical normal distribution. And then we can look at x6, and here we can see some multiple peaks, so it might be bimodal possibly. But it just kind of overall looking at this, we can see we have pretty inconsistent data set, and we can tell this because we have a pretty large variety of points here. We can see some negative numbers close to 0, like the negative 0.07, and then we have some larger positive numbers like 0.53. So basically just showing that we don't have much consistency and we have low reliability with it. Then here we're looking at the bivariate analysis of our x variables compared to y1. So I just want to point out the our r squared of 0.3175, so 31.75%. This is a relatively low value. The closer the r squared value is to 1, the stronger the model is. So we have an adjusted r squared of 0.2931, so that's still pretty low, but it does confirm what our sum x is showing us. The sum x coefficient is the 0.14134, and it's basically telling us that each unit increases, it's predicted that y1 will have an increase of what the sum x is. So y1 will increase by 0.01434. Okay, and then we have the graph on this side. Here, this graph is just a visual representation of the sum of the x variables and the y variables. So the blue line is the linear regression line that we saw. The sum x is, again, the 0.14. And we do have a positive slope, so that's telling us that as the sums of x increase, so does y. And then we have the gray shaded area around that. That's representing the confidence interval, telling us about our uncertainty. And then you can see the band gets wider near the ends, and those are our extremes because we have fewer data points, so that is leading us to less certain predictions. And then this pattern is just suggesting that we have moderate positive linear relationship, and the relationship is statistically significant because we do have a p-value of 0.001186. Sorry, so that is telling us that it is statistically significant. Next, we do have an analysis of multiple linear regression model. We have the intercept and the most predictor values are not statistically significant except for x5. We can see that that one is significant with the value of 0.0438. The R squared is moderate with a value of 0.5062, which is like 50.62%. And then we do have an adjusted square value of 3491. So that is accounting for the outliers and the predictors, so it is a little bit lower. And then we have an F statistic of 3.22 that's telling us that the model is statistically significant because we can see that the p-value is less than 0.05. So with a p-value of 0.016. So then looking at, let me get my laser pointer. Looking at this chart here, we're looking at the VIF. So that is the variance inflation factor, and that's just a measure that's used to detect multicollinearity among the predictor values in a regression model. So it's showing us how much a variable is inflated because of its correlation with with other predictor variables. None of the variables have a very high VIF. All of the values are kind of around 2, so that's telling us that there's moderate to low multicollinearity. If we had any values like greater than 5, then we can look at kind of removing some predictors. So then on this side here, we did another analysis predicting y1 based on the sum of the x's and f3. So we can see that sum x is statistically significant with a p-value of 0.00157, and that's telling us we do have a meaningful effect on y1. On the other hand, F3 is has a pretty high p-value, so that's telling us it does not contribute much to predicting y1, and it's not statistically significant. And then the R squared value is 31.83%, and that's a pretty decent amount. Then we have the F statistic showing us that the model is statistically significant overall because of this p-value, but because we saw these values up here, we can tell that just because it is statistically significant overall, but for the most part, sum x seems to be the only significant predictor. F3 is not significant. And then down here we have the VIFs again, and for both sum x and F3, and we do see that they are pretty low and they're close to 1, which means the multicollinearity is not a concern, and there's no evidence of strong correlations between sum x and F3. This model shows to not be really suffering from multicollinearity, and both sum x and F3 are showing that they're pretty good, like they're providing like unique good information towards the model. Then continuing on with our multiple regression, we do have this graph here. So this graph here is showing different groups that are affected by the relationship between y1 and the sum of x variables. So each line represents how y1 changes sum of x. Group 2 is showing a strong positive slope. You can see group 3 in the green, it's almost flat. Group 4 in the blue shows a moderate positive slope, and then lastly group 5 shows a slightly positive slope. So this is telling us that the group group membership is an important factor in understanding like how y1 is relating to the sum of other variables. And this pattern is suggesting that a simple linear model might not tell the whole story. And the relationship between the variables depends on like which group we're looking at. So because of that, I went ahead and did a Box-Cox transformation to see if transforming our data will make it more normally distributed. So this plot here is showing the relationship between the different lambda values on the x, and then on the y we have the log likelihood. We have the log likelihood. So the peak of this curve is representing the lambda that would make the data follow normal distribution at the closest. So you can see that's going to be a lambda of 1.232323, and that's a pretty good value because it is close to 1. And a lambda of 1 means that there's no transformation needed to the original data. But since it is a little bit off of 1, a transformation would help normalize this data. So here we have the output of fitting the linear regression model. We do see that sum x and the intercept are both statistically significant. We have an R squared of 33.8%, which is telling us, we have the R's value of 33.8%, and that's telling us that 0.08% of the variation in the transform dependent variable is explained by that sum x. So the Box-Cox transformation does appear to improve the model, and that's doing that by addressing things like the non-normality in y1. Then lastly, this graph here is showing the results of the Box-Cox transformation. So it is showing that there is some natural variability in our data. And what's particularly interesting here is how this compares to the original bivariate plot. The relationship still is showing a positive, like a positive slope, but the transformation helps kind of make a relationship more linear and is spread and the spread of points are more like consistent throughout the range of x values. So that's kind of what we want to see here in a Box-Cox transformation. And then I listed my references here. If you have any questions, please let me know. Thank you for watching.